Hello my scholars, you are welcome to my school YouTube channel and my name is Frank. In today's video, we shall be discussing about the application of lens in optical instrument. So relax, do not go anywhere, I will be right back. You are welcome back to my school YouTube channel. Like I said earlier, in today's video, we shall be learning about the application of lens in optical instrument. So before we begin with the lesson proper, let's quickly run through the objective for today's lesson. So objective number 1, construct I, box camera, 2, compound microscope, 3, telescopes, and 4, film projector. Then 2, explain the formation of images by the camera and the projector by tracing rays of light through them. 3, explain the role played by some parts of the eye in the formation of image on the retina. Then 4, compare and contrast the eye and the camera. Then 5, state the defects of the eye and their causes. Then 6, identify the type of lenses for correcting the various defects of the eye. Then the last but not the least, trace the paths of light rays through simple and compound microscopes and telescopes. So let's begin with our lessons. So before we begin properly, I just mentioned optical instruments. So what are optical instruments? So optical instruments are devices that manipulate light to enhance vision or capture images. So basically what we are going to be doing in this lesson is just to show the various devices where lens find application. So the first one is the simple microscope, also known as magnifying glass. Okay, so the simple microscope or magnifying glass is a converging lens. Okay, now remember that another word for converging lens is convex lens. Okay, so both of them are used interchangeably. So the simple microscope is a converging lens used to produce a magnified and virtual image of small objects. So also take note of the type of image form, virtual. Okay, now the object is placed between the principal focus and the optical center of the lens brought very close to the object, and a magnified virtual and erect image is formed. So above here on the side of the screen is the image of the simple microscope. So you can see the object here between the focal length or the principal focus, okay, and the optical center, right? And this is the image form. Though the image form is virtual, but the image is magnified, meaning that the height of the image is more than the height of the object, as you can see on the diagram. So now let's talk about the uses and or application of the simple microscope. Now one of them is for reading small print, okay, and the second one it is used for studying biological specimen, okay, such as that hand lens that you normally use in your biology lab. Okay, so that is just a simple microscope. So let's move to the next slide. So on the next slide there, we are going to be talking about the compound microscope. So the compound microscope is another version of the simple microscope, okay, or like a better version of the simple microscope. So the compound microscope consists of a combination of two converging lenses. One of the lenses is called the objective lens and the other is called the eyepiece. Okay, so the objective lens is nearer the object, and through the eyepiece the final image is seen. The two lenses are of short focal length, but the eyepiece has a comparatively larger length. So as you can see in the diagram on this side of the screen, this is the diagram of a compound microscope, and these are the two converging lenses. So this is the objective lens and this is the eyepiece. You should also take note here that the focal length of the eyepiece is larger or is more than that of the objective. Okay, so from the diagram, OA represents the object, which is here, OA. Okay, so this represents the object, while I1 represents the re-image, which is this, while I2 represents the virtual image, which is this. Okay, while F0 is the principal focus of the objective lens, okay, and IE is the principal focus of the eyepiece. So below is just how the microscope or the compound microscope helps in magnifying the image of object. Okay, so the object is placed in front of the objective at a distance greater than its focal length. Okay, so if you look at the focal length, this is the distance between the principal focus and the optical center, gives us the focal length, right? So if you check from here to here, from this point to here, and from this point, that is from the optical center to the object, discover that the distance from the optical center to the object is more than that from the optical center to the principal focus. So just take note of that. Okay, so the object is placed in front of the objective at a distance greater than its focal length. Then a real and magnified image I1 is formed in front of the eyepiece at the point P. So this is the front of the eyepiece, and this is the real image that is formed. Now the eyepiece is adjusted until the position I1, which is the image that was formed, is nearer to it than its principal focus. Then IV, in this way, the eyepiece function as, let's move to the next slide. So the eyepiece function as a magnifying glass, and the magnified but virtual image I2 is formed at D. Okay, so the magnifying power M of a compound microscope, this is very important, is just the product of the magnification produced by the two lenses. So the two lenses here are the objective and the eyepiece. So that M, which stands for the magnifying power of the compound microscope, is equals to M1, which is the magnification produced by the objective lens, times M2, which is the magnification produced by the eyepiece. From the diagram, M1 is equals to BG all over OA. Now, BG here represents the image height, okay, that is, or the image size, or the distance of the image from the lens, okay. So, OA represents the object height, BG represents image height, and OA represents image height, okay, for M1. Then M2 is equal to DH all over BH, right? So the BH here represent, because now for the eyepiece, the image produced by the objective lens now serves as an image for the eyepiece. So in this case, it becomes BG for the image height, while DH is the virtual but magnified image that was produced. Okay, so if we combine these two together, since the magnifying power of a compound microscope is M1 times M2, so if we combine these two together, we'll be having BG all over OA times DH all over BG. So BG will cancel out BG, so that at the end of the day we'll have DH all over OH. Okay, so let's talk about the uses and application of the compound microscope. So one of the uses of the compound microscope is that it is used for studying tiny objects, and this actually helps us to see details, okay, to see details up close. All right, now one advantage of the compound microscope is that it produces a higher magnification than that obtained from a simple microscope. But one thing that almost wanted to serve as a disadvantage of the microscope is that the final image is inverted, right? But this is, however, not a problem in studying tiny objects, since the observer can adjust the eyepiece, okay, to actually capture or to see the image produced properly. Let's move to the next slide. For the image to be at its near point of vision. So in the subsequent, as the lesson progresses, we will get to know the meaning of near point of vision. Okay, so below are just some work for us to put some of all those formulas that we have seen into practice. So let's begin with question 1. An object 2.5 mm, that is millimeter long, is viewed through a convex lens of focal length 10.0 centimeters, head close to the eye. A magnified image of the object is formed 30.0 centimeter from the lens. Now take note of this question, that here the convex lens is used as a simple microscope, and remember that a simple microscope will produce a virtual image. Okay, so take note, V in this case will be negative. So here we are asked to solve 1, distance of the object from the lens, 2, size of the image, and 3, power of the lens. So let's move over to the board to provide answer to this question. So remember, we are still talking about lens. So here the lens formula is still applicable. Okay, so lens formula is 1 over F is equals to 1 over u plus 1 over v, right? But here we are looking for object distance, so we are looking for u. So v is given to us to be equals to 30.0 centimeter. But remember, for a magnifying glass or for a simple microscope, the image produced is virtual. So this is going to be negative. Then f still remains positive, okay? So that is 10.0 centimeters. So here we can actually solve for u, which is the distance of the object from the lens, right? So let's substitute the values that are given to us into this formula. So here we have 1 over f, let's just repeat the formula again, is equals to 1 over u plus 1 over v. So here we'll be having 1 over 10 is equals to 1 over u, then minus, because our v is virtual, minus 1 over 30. Of course, here we are supposed to have plus then minus 30, but minus is stronger than plus, so minus we push away plus, right? So since we are looking for u, we just make 1 over u the subject of formula. So that 1 over u is equals to 1 over 10 plus 1 over 30. Okay, so here the LCM of 10 and 30 is 30. So 10 into 30, that will give us 3. Then 3 times 1, that will be 3. Then our plus, which is this. Then 30 into 30, that will give us 1. 1 times 1 is 1. So that we'll be having 4 all over 30, right? But we are looking for u and not 1 over u. So we are having, let me rewrite this part. So we are having 1 over u to be equals to 4 all over 30. So to get our u, we just say u is equals to, then we invert this. So we'll be having 30 all over 4. Okay, so let's divide. So how many 4 is in 30? First of all, that will be 7. That is 28, remember 2. So we drop a point here and put 0 in front of the 2. So the 2 becomes 20. Then 4 into 20, that will give us 5. Okay, so the distance of the object from the lens is equals to 7.5 centimeters. So we have answered question I. Now let's move to question II, the size of the image. So since we are calculating for the size of the image, okay, remember that magnification is equals to V all over U, right? Which is also equals to H1 all over H2, right? So HI there represents the height of the, or the size of the image, okay? While H2 here represents the height or size of the object, right? So let's substitute. So here we know our V here to be equals to 30 and our U to be equals to 7.5, and this will be equals to H1 all over. Now remember that the object height was given to us in the question to be equals to 2.5 millimeter. Okay, so we'll put 2.5 here. Okay, 2.5 millimeter. Now remember that here we have centimeter here, we also have centimeter here, so they will cancel out. So at the end of the day, H1 is equals to 30 times 2.5 divided by 7.5, right? So I just cross multiply and make H1 the subject of the formula, which is the size of the image, right? So 7.5 here is 1 and 7.5 here is 4. So H1, which is the size of the image, is now equals to 4 times 2.5. And 4 times 2.5, that will be equals to 10.0 mm. Remember, our mm here still remains, okay? So the height of the image, or the size of the image, is equals to 10.0 mm. So let's solve question III. So this is question II. Okay, so which is the third one. So for the third one, we are asked to calculate the power of the lens. Okay, we are asked to calculate the power of the lens. But for this question, the focal length is given to us in centimeters. So in that case, the power of the lens here is going to be 100 all over f. Okay, because the focal length is given to us in centimeter. Now, had it been is given to us in meter, then here would have been 1. I think the essence of this 100 is so that the conversion can be done directly. Okay, so here we now have 100 divided by 10. So 100 divided by 10, that will be equals to 10 diopter. Okay, give us 10 diopter, or let us say 10D for diopter. So the power of the lens is equals to 10 diopter. Now remember here, our solution is positive, and the reason for that is because we are talking about convex lens, right? Had it been it was concave lens, then this place would have been negative. So that is very important to take note of. Okay, so let's return back to the screen to continue with the examples. So let's move to example B. In a compound microscope, the initial image is twice the object, while the final image is 4 times the object. Calculate the magnifying power of the microscope. So this you don't actually need to solve, okay, because in this question, if you check very well, we are given the magnification produced by the objective lens, okay, but we are not given the magnification produced by the eyepiece, right? But we are actually given the magnifying power of the microscope, which is this final image, okay? So the magnifying power of this microscope is equals to 4, okay? You don't have to solve anything, but if you want to solve, for example, you are asked to calculate for the focal length, okay, or the magnification produced by the eyepiece, right? Then in this case it would have been 4 divided by 2. Okay, so that will give you 2. Then going by the magnification formula, that would have been m1 times m2. So 2 times 2, that will also be equals to 4. So, but in this case, you don't have to bother yourself because they said the final image produced by the compound microscope. So that is the magnifying power of the microscope. So that makes the answer to this question equals to 4. Okay, so let's move to the next slide to continue with our lesson. So here we are going to be talking about another instrument again where the lens also find application, and that is the astronomical telescope. Okay, so the astronomical telescope is the simplest type of telescope. It consists of 2 converging lenses mounted so that they have a common axis. The objective lens has a long focal length, while the eyepiece has a short focal length. So this is more or less like the opposite of the compound microscope. Okay, so this is to ensure that the telescope has a high magnifying power. So below is the diagram of the astronomical telescope. So F0 represents the focal length of the objective, while FA represents the focal length of the eyepiece, while I1 is the first image produced, which is F0B, while the final image produced is I2, which is DG, while F0 is the principal focus of the objective, while the FA is the principal focus of the eyepiece. Okay, I've said that earlier. Now here, magnifying power is not equals to the magnification produced by the objective lens times the magnification produced by the eyepiece. No. So if you check the diagram very well, you can see a little angles here and also here. So magnification here is equals to beta all over lambda, which is the angle produced by the eyepiece over that angle, that small angle produced by the objective lens. Let's move to the next slide. So the magnifying power is also called angular magnification. Okay, so don't miss this up. Magnifying power is also called angular magnification. So when you are asked to calculate angular magnification, definitely they are asking you to calculate for magnifying power. Okay, so let's just describe how the astronomical telescope works. So parallel line rays from a distant object enters the objective, and these rays are parallel rays are inclined to the principal axis at a small angle, like we saw in the diagram in the previous slide. So a reinvected and diminished image I1 is formed at the principal focus F0 of the objective. The eyepiece is adjusted almost like the compound microscope. The eyepiece is adjusted so that the image I1 is closer to it than its principal focus, Fe. In this way, the eyepiece functions as a magnifying glass and forms the final image I2, which is magnified, virtual, and inverted. Okay, so here the lenses can be arranged such that the principal focus of objective or the objective lens F0 coincide with the principal focus of the eyepiece Fe, With this arrangement, the final image is at infinity. And in this arrangement, we say that the telescope is said to be in normal adjustment. So sometimes you can be asked, when is a telescope said to be in normal adjustment? So you can tell them that a telescope is in normal adjustment when the lenses are arranged in such a way that the principal focus of the objective coincide with the principal focus of the eyepiece. Now remember that the objective here, you are talking about a lens too, right? Because for the astronomical telescope, it also consists of two lenses. One they call the objective and the other they call the eyepiece. Okay, so the telescope is said to be in normal adjustment, okay, when the lenses are arranged in such a way that the principal focus of the objective lens coincide with the principal focus of the eyepiece. So let's move to the next slide to continue with our lesson. So magnifying power, okay, for the astronomical telescope is also given as f0, which is the principal focus of the objective, all over fe, which is the principal focus of the eyepiece. Then we also have the distance of separation between the two lenses, okay? And remember that the distance of separation between the two lenses actually gives us the length of the microscope. So sometimes we can as well be asked to calculate it. So the length of the microscope or the distance of separation between the two lenses is given as d is equals to f0 plus fe. So take note of this, where f0 is equals to the principal focus of the objective lens, then plus the principal focus of the eyepiece. So now let's talk about the uses of the astronomical telescopes. One, it is used in viewing distant objects such as the stars and planets. So these are normally used by stargazers, okay, to view stars. So the inverted image produced by astronomical telescope can be tolerated when viewing stars. Okay, so this is like one of the advantages of using the astronomical telescope, right? The inverted image produced by the astronomical telescope can be tolerated when viewing stars. It is a real disadvantage when viewing the Earth, like you cannot use it as a terrestrial telescope. So it's a real disadvantage when you are using it for viewing objects on the Earth. So let's move to the next slide. So on the next slide here, we are going to talk about another form of telescope, which is called the Galilean telescope. So the Galilean telescope consists of a converging lens of long focal length as the objective and a diverging lens of short focal length as the eyepiece. So the Galilean telescope actually combines or consists of the two types of lenses, okay, of the two types of lens. We have the convex lens serving as the objective, and we also have the diverging lens serving, or the concave lens serving as the eyepiece. So the two lenses are mounted such that they have a common axis, and the distance between them, this is also worth taking note of. So the distance between them is still the same thing as the length of the Galilean telescope. So the distance between them equals the difference between their focal length. Okay, the distance between them equals the difference between their focal length. So the diagram below is the diagram of the Galilean telescope. So this is the objective lens, okay, which is a converging lens, and this is the eyepiece, which is a diverging lens. So let's describe how the Galilean telescope works. Now, one, parallel rays from a distant object enters the objective and they ought to converge at its principal focus f0 to form re-inverted images. Let's move to the next slide. To form re-inverted images. Before the rays converge at the principal focus f0, they are intercepted by the diverging lens, which causes the rays to diverge and emerge as a parallel beam, as you can see in the diagram below. So a virtual, upright, and magnified image is therefore formed at infinity. With the above arrangement, the Galilean telescope is said to be in normal adjustment. It is possible to adjust the Galilean telescope so that the final image is formed at the near point. Let's move to the next slide. Now, magnifying power of the telescope is given as f0 all over fe, where f0 is equal to focal length of objective and fe is equal to focal length of eyepiece. Now, one advantage of this Galilean telescope is that it produces a magnified, upright, and virtual image. So let's talk about another type of or another kind of telescope, but this time around this telescope is used on Earth, and the telescope is called the terrestrial telescope. So the terrestrial telescope is a modified astronomical telescope with an additional lens in between the objective and the eyepiece. The aim is to invert the image to make it upright. So this is the diagram of the terrestrial telescope. So this telescope actually consists of 3 lenses. Okay, so but the 3 lenses are converging lenses. Okay, so we have the objective and we have the eyepiece, but in between the eyepiece is another lens called the inverting lens. And the essence of this inverting lens is so that it can invert the image, okay, produced by this telescope to make it upright. Let's move to the next slide. Now, the additional lens is called inverting lens. So how does this work? So the objective lens forms a real and inverted image of the distant object at its principal focus. The inverting lens is placed so that the image form is at 2f from it. So the f here stands for focal length. So the inverting lens is placed so that the image form is at 2 times the focal length from it. Then another image is formed at 2 times the focal length from the inverting lens on the other side of it. This image is re-inverted to become upright. This second image becomes an object to the eyepiece. Its image is formed at infinity. Now, one of the advantages of this telescope is the production of upright image, but it also has a disadvantage. And that disadvantage is that the inverting lenses extends the length of the telescope by 4 times the focal length, making it too long. So the disadvantage is that this telescope, this terrestrial telescope is long, is very long. Okay, that is one of the disadvantage of this telescope. But apart from that, it's a very good telescope in the sense that it produces an upright image. So this is where we end the video for the preview of today's video lesson. I believe you enjoyed it and you learned something from it, but you can watch the complete video by simply clicking on the link in the description below, and that will take you to my school website. In the my school website, you will have to subscribe to enjoy the complete video, and in the complete video you will learn more about other instruments, okay, that incorporate lenses in its application, okay, such as the prism binoculars, right? You also learn about the human eye, the simple camera. You will learn how to compare and contrast the eye and the simple camera and many more. So I believe you enjoyed the preview of the video you just watched. If yes, please do not forget to hit the like button, click on the subscribe button, and lastly, tap on the notification bell to get informed as soon as we release the next videos.